In this video, I'm going to talk about upper motor neurons. So upper motor neurons, which are different than the motor neurons we talked about before, which are the lower motor neurons. Now, when we talked about the lower motor neurons, we talked about how they have their somas either in the brainstem or in the spinal cord, and how they send axons out through nerves in the peripheral nervous system to synapse on and control skeletal muscle cells, to tell those skeletal muscle cells when to contract. And we talked about that the lower motor neurons that pass through spinal nerves primarily control muscles of the limbs and the trunk, and lower motor neurons that pass through cranial nerves primarily control the skeletal muscles of the head and the neck. But now we're going to talk about the upper motor neurons, because it turns out that while the lower motor neurons are controlling the skeletal muscle cells and telling them when to contract, upper motor neurons are the ones that are controlling the lower motor neurons and controlling their activity. The somas of the upper motor neurons are found mainly up in the cerebral cortex, way up here in the brain on that outside surface of the cerebrum. And their axons descend down to synapse on lower motor neurons in the brainstem or in the spinal cord. And so information flows from up here, mainly in the cerebral cortex, down these axons to the lower motor neuron somas, and then out the axons of the lower motor neurons to actually reach the skeletal muscle cells to determine when they'll contract. And we can divide up the upper motor neurons into some different pathways or tracks, depending on if they go all the way down into the spinal cord to synapse on lower motor neurons, or if they go a shorter distance to the brainstem to synapse on lower motor neurons. So first, let's look at these longer upper motor neurons that send axons all the way down into the spinal cord. So let's take the brain and the spinal cord here, and I've got a little larger illustration of that. So here we have the cerebrum up top. Here is the brain stem, and behind it is the cerebellum. And then beneath it is the spinal cord. But first, let's think about a lower motor neuron here in the higher part of the spinal cord on the left side, because we're looking at the front here. So this would be the left side. And the lower motor neuron will have its soma inside the spinal cord, and then it'll send its axon out through spinal nerves and the smaller branches that it branches into until it synapses in some muscle that it's going to control some of the skeletal muscle cells in that muscle. The upper motor neuron that's going to control this lower motor neuron is going to start somewhere way up in the cerebral cortex here, in that layer of gray matter on the outside of the cerebrum, and its axon's going to kind of travel down through the deep white matter of the cerebrum, and then it's going to travel down through the brain stem, through the midbrain, then the pons, then the medulla, and then at this point, where the brainstem meets the spinal cord, at the bottom of the medulla, most of these axons are going to cross over to the other side, and then they're going to travel down the other side of the spinal cord until they reach this lower motor neuron to synapse on it and control it. So this pathway, this collection of axons that are upper motor neurons traveling from the cerebral cortex to lower motor neurons in the spinal cord, we call this the corticospinal tract. Let me write that out. Cortico, which means it starts in the cerebral cortex, and then spinal, which means that it ends in the spinal cord. So it's going from cerebral cortex to spinal cord, so we call it the corticospinal tract. And a tract is a collection of axons traveling together through the central nervous system. Now, because most of the axons that make up the corticospinal tract travel down one side of the brain and then cross over to travel down the other side of the body, what we see is that if there's dysfunction of these axons of the corticospinal tract on one side of the spinal cord, we usually get weakness of muscles on that same side. But if we see dysfunction of the corticospinal tract on the other side of the brain, either up here in the cerebral hemisphere on this side or on the brainstem on this side, we usually see weakness on the other side of the body, so that the right side of the brain controls the left side of the body in terms of controlling the skeletal muscles, for the most part. Things get a little more complicated for the lower motor neurons in the brainstem. So let me just draw one lower motor neuron over here on the left side, and it's going to send an axon through a cranial nerve to a skeletal muscle in the head or the neck. And let me actually draw it the same kind of thing on the other side, sending lower motor neuron axons through the same cranial nerve to the other side to a muscle on the other side of the head or the neck. There are going to be different upper motor neuron somas up here in the cerebral cortex, and many of these are going to send an axon down in a similar way as the corticospinal tract, and similarly they're going to cross over and innervate these lower motor neurons on the other side of the brainstem. However, for lots of these lower motor neurons that pass through cranial nerves, what we actually see is that there's often also upper motor neuron axons that come down and innervate lower motor neurons on the same side. So instead of having most of the upper motor neuron axons cross from one side over to the other side, like we see with the corticospinal tract, for a lot of these lower motor neurons that control muscles of the head and neck, we see that one side of the cerebral cortex often sends upper motor neurons to both sides of the brainstem. So we give this tract carrying the upper motor neuron axons to lower motor neurons in the brainstem a different name than the corticospinal tract because we're not going to the spinal cord. We're still starting at the cerebral cortex, so we call this pathway, it starts with cortico as well, cortico, but instead of going to the spinal cord, we're going to the brainstem. And it would make sense to call this the cortico-brainstem tract, but instead it's got an older name for the brainstem, which was the bulb. So we call it the cortical bulbar tract. Cortical bulbar tract. And that includes these upper motor neuron axons that are going to innervate lower motor neurons in the brainstem. And because the wiring's a little bit more complicated in the brainstem, we can get some different patterns of weakness with abnormalities of this pathway. So I'll save some of the details of that for later because it gets a little complicated. Dysfunction of either the lower motor neurons or the upper motor neurons can cause weakness. Because if there's a problem with the lower motor neurons and they're not telling the skeletal muscle cells to contract, then there isn't going to be as much contraction and we can see weakness. But it turns out that if there's a problem with the upper motor neurons and they're not telling the lower motor neurons to tell the skeletal muscle cells to contract, we also don't get as much contraction and we can see weakness. In another video, we talked about the lower motor neuron signs, these other things we can see in addition to weakness or even without weakness if there's some problem with the lower motor neurons. And it turns out there are upper motor neuron signs. And just like with the lower motor neuron signs, the upper motor neuron signs can occur with weakness or even without weakness if there's abnormalities of these upper motor neurons. And this can help us understand if a patient has weakness, whether the problem is in the lower motor neurons or in the upper motor neurons. The first of these upper motor neuron signs we call hyperreflexia. Let me just write that out. Hyperreflexia. And this is an increase in the muscle stretch reflexes. So let me just write MSR for muscle stretch reflexes. So this is actually the opposite of one of the lower motor neuron signs, which is hyporeflexia, where we see a decrease in the muscle stretch reflexes. So that if this patient over here had some trouble with their corticospinal tract, their upper motor neurons coming down from the cerebral cortex to the lower motor neurons in the spinal cord, when this doctor right here taps this patient in the tendon below the kneecap with a little rubber hammer, instead of less response, instead of less contraction of these muscles, we could see more response. We could see this very brisk kicking out of the leg because these muscles kind of over-respond to that stimulus. The cause of hyperreflexia with upper motor neuron dysfunction is not totally clear, but apparently when the muscle spindles, these little receptors in skeletal muscle that detect muscle stretch, when they're activated and the somatosensory neurons carry that information back into the spinal cord to excite the lower motor neurons to cause the muscle contraction, that is the muscle stretch reflex. Apparently, without periodic stimulation of the lower motor neurons from the upper motor neurons, the lower motor neurons may become kind of super sensitive so that the normal excitation of this somatosensory neuron causes this very exaggerated response of the lower motor neuron, and you get a bigger reflex. But we definitely don't understand the whole process of why this happens. The next upper motor neuron sign is called clonus. Clonus. And clonus involves rhythmic contraction, of antagonist muscles. Antagonist muscles. And those are muscles that have the opposite effect on a joint. So for example, on this patient here, and on you, there are muscles in the front of the shin that cause you to pull your toe up like that, pull your foot up. And there are muscles in the back part of the leg here that cause you to push your foot down like you're pushing on a gas pedal. We call those antagonist muscles because they cause the opposite movement. And what we see with upper motor neuron dysfunction is that if this doctor were to grab this patient's foot and rapidly pull it upward, the foot may go into this involuntary movement where it starts coming up and down and up and down and up and down. And we call that clonus. And the cause of clonus is probably just hyperreflexia. Because if the doctor here rapidly pulls up on the foot, there's stretching of these muscles in the back of the leg here, and that can activate the muscle stretch reflex, causing these muscles to contract, which then makes the foot go down, and that can actually stretch the muscles on the front of the leg here, triggering their muscle stretch reflex, and then the foot comes up. And basically each time the foot goes the other direction, it stretches the muscles on the other side, so that the muscle stretch reflexes of the antagonist muscles are triggering each other. The next upper motor neuron sign we call hypertonia. Hypertonia. And hypertonia means increased tone of skeletal muscles. And this is another one that's an opposite of one of the lower motor neuron signs, where we can see hypotonia. We can see decreased tone of skeletal muscles. And we really don't understand why we see an increased tone of skeletal muscles when there's upper motor neuron dysfunction. One possibility is that it's related to the hyperreflexia, that if this doctor takes this patient's leg and tells them to try to relax it as best they can, and they start moving that leg around, it gives more resistance. It isn't as relaxed as it normally would be. That might be because the pulling on the muscles stretches them and activates the muscle stretch reflex. But we're not totally sure about this. And the last upper motor neuron sign has a long name. It's called the extensor plantar, which just refers to the foot, the bottom of the foot. Extensor plantar response. And what this long name means is that if you take a hard object, like they're showing in this picture here, and what we usually use is the hard end of a reflex hammer. And what you do is you scrape up along the bottom of the foot with the hard end. Not really hard, but just enough so that a person can feel it. And the normal plantar response is not extensor, it's flexor. So just like they've drawn here, if you normally scrape something hard up along the bottom of the foot, the toes all flex. They come down in the direction of the bottom of the foot, like they're showing here, this way. But with upper motor neuron dysfunction, we can see this abnormal extensor plantar response, where we scrape up along the bottom of the foot, and then the toes go into extension. They go the other direction, away from the bottom of the foot. So we call that the extensor plantar response. And it also has a person's name, Babinski, so it's called the Babinski sign, because this person described this. And we really don't know the mechanism of the extensor plantar response when there's dysfunction of the upper motor neurons, but it is something that we commonly see.